Hey everyone, in these notes we're going to be looking at 2D projectile motion, stuff moving not just in X, side to side, not just in Y, up and down, but something moving kind of at a combination. So this is your golf ball being hit, your football thrown, your cannonball launched, your diver running and jumping off a cliff, things like that. And so really our objective here to start us off is we're going to be applying our knowledge of vectors, constant acceleration, and constant velocity to just solve problems, analyze phenomena. And I've kind of started us off here with kind of two little intro sentences. And the first is that objects that are projected, so launched, into the air at an angle follow a parabolic path. Now, we're pretty familiar with this parabolic stuff already. It's a quadratic. We've been looking at this with some of our labs already, but that's just the pathway they'll follow. We'll draw it in a moment. And here's the weird thing. The x and y components, or the pieces, of the displacement and velocity are independent of each other. So what the heck does that mean? That really means that the x displacement is separate from the y displacement. They're not going to affect each other, as odd as that sounds. So no matter how far something moves in the x direction, that doesn't affect how much it moves in the y direction. Those are split from each other. And so we have the x displacement, the y displacement, the x velocity, and the y velocity. It's four things, and we can essentially break it down so we're looking at the y things separate from the x things. And now what we're going to add a little bit more actually here. And so what I want to put is that the x component, so the x component is moving at a constant velocity. It's moving at a constant velocity. I'm going to underline that even. And the y component, so the y component of velocity, this should have been of velocity, and the y component of velocity is constantly accelerating. And this is due to gravity. Okay, so we kind of have two different things going on here. And I do want to say that the x component constantly moving at a constant velocity is only because we ignore air resistance. The air is actually in the way. Something moving through the air is having to push the air out of the way. The air is resisting it a little bit. And so, yes, it is technically slowing down a little bit in the x direction as it moves. But because we ignore air resistance, it's not going to slow down in the x direction. It is going to speed up or slow down in the y direction though. And so I want to make a little note here. Note, we are ignoring air resistance. The question says, oh, how would air resistance affect this differently? Well, you'd say, oh, well, this constant velocity thing in the x direction would change. It would end up being a small constant acceleration. It would be slowing down. So let's look at what the heck this actually means. So I'm going to go down, I don't know, 1, 2, 3, 4 lines, something like that. And I'm just going to have maybe something is like a little ball is getting launched. And so let's say it's going to go that way. And what this really means then is it's going to go in this direction, but then it's going to slow down and reach kind of some peak, and then it's just going to fall back down, is kind of the idea here. And it's going to be accelerating, so it should be getting steeper and steeper and steeper. And what I want to do here is I'm going to break it down. So we actually have a little part here. This is the x velocity. This is the total initial velocity. And then this would be actually like the y part of the velocity. And I'm going to label this v y naught. And when we're looking over here at this point at kind of the top of wherever the ball is, well, it still has the same x velocity because, again, it's constant velocity. It's not slowing down in x. But right here at the top, the y velocity is actually 0. So in the y direction, it's like stopped, essentially, and it's going to turn around to fall back down, kind of like the red rocket. And then at some later point, maybe we look over here, it has this very large velocity. It's actually bigger than what it initially started with, is kind of what I'm trying to say here. And so it has this larger, or it has this same size x velocity, but now the y velocity is actually larger because it's been accelerating longer and longer as it's been falling. So it's fallen farther down than it moved up, is kind of what this is saying. And so what we're going to be often doing in problems like this is kind of setting up a triangle where we go, okay, well, here's our velocity, and then here's kind of our angle theta here. We go, oh, well, cool. We can set up this little triangle. We got the x part, we got the y part. And so we could use sine or cosine or tangent, and we can kind of compare these. And so we'll use like trigonometry really to separate these components. And so I want to make a little note here. We use sine, cosine, or tangent to separate components. Oops, I can spell. That was worse. ARATE. And so we have to do this. We'll have to separate the components so that we'll end up looking at the y part and the x part. We'll actually look at these two parts separately. And so let's actually take a look at how the heck we actually do that. And so I just want to kind of remind you right here that we have this equation sheet that we've been using a lot so far. We have these three equations, and we can look at these three equations in the x direction, and we can look at these three equations in the y direction. And so looking at these in the x direction, just kind of letting you know here. If we look at these in the x direction, well, there's no acceleration in the x direction, and so the final velocity is the initial. That's kind of a dumb one to look at. But if I look at this second one here, again, there's no acceleration, so this whole term is 0. Okay, and if we say wherever the heck the thing is starting is 0, well, we can call this 0 as well. And so this equation has become x equals our initial x velocity, our initial x velocity times time. So if I rearrange this a little bit, we get distance over time is the x velocity. And I don't even need to call it just the initial. I can drop the not because it's not changing. And so really, this second equation just becomes velocity is distance over time in the x direction if there's no acceleration. And so here's how we're going to set up every problem we do for projectile motion. We're going to set up kind of a horizontal section, and then we'll set up a vertical section. And we're essentially going to make kind of a little T-chart here. And really, I probably only needed to go down, 8 or so lines and something like that. Maybe even a little less than 8. And so we have as our first equation that the x velocity is just how far it goes in x over time. And looking at my triangle here, well, if I wanted to find just the x part here, well, we would say that cosine of the angle would be the adjacent over the hypotenuse. So we would end up having that it would be this Vx over V. All right, terrific. These are the only two things we'll really ever set up in the horizontal. Now, in the vertical, we have all of three of these equations because there is an acceleration. Gravity's always, every single point along the way, gravity's pulling down on this thing every single bit along the way. And so we still have all those same equations. So we have Vy, and I'm changing it from your equation sheet from x's to y's. So our final velocity is our initial velocity plus the acceleration times time. I then have that our y distance is wherever it starts in the y, plus the initial y velocity times time, plus 1/2 the y acceleration, which is gravity, times time squared. And then we have that our final velocity is equal to our initial velocity squared plus twice the acceleration times the difference between where it starts and where it ends. And now, though, if we used cosine to find the x, we would end up using sine to find the y because sine is opposite over hypotenuse. And so if this is my angle kind of in this little corner, the opposite side would be the y part here. And so we'll also add that sine of our angle is the initial y velocity over the final velocity. And these really are the equations that we'll be using all the time. We're going to be using these over and over and over, but kind of in all sorts of different ways so that we can kind of solve different questions depending on what you're given. So you might end up needing to find the time in one of these and then plug it in, I don't know, here and here to find how far it's gone in the y direction. It really depends, again, on what the question is giving us. And so let's make kind of two final little notes here, and then we're really done. And our next video will be actually looking at and doing a practice problem, kind of looking at a cannonball, seeing if it makes it over the castle walls. And so the last thing I want to put here is that often we can use, and this is just kind of a general rule, this isn't always what happens, but oftentimes we can use the vertical portion, and its equations to solve for time. This is just kind of a weird thing I've noticed. Oftentimes, we'll just use the vertical portion to solve for time. And then you maybe just plug time in here. And if you know the x velocity, you can find like how far something's gone, for instance, because then you could just solve for x is kind of the idea. The last thing I want to make a note of is we will always, pretty much always, we'll always have to use sine, cosine, or tangent. Okay, now this is kind of a strange one. This is actually something that a student told me. This is kind of what their short note was on how to do really well at problems like this all the time. And so this is actually how to kick butt at 2D kinematics problems. And step one. Step one is draw a picture. Draw a picture of what's happening. Step two is draw the triangle for the object's motion. And do sine and cosine. Sine will get you the y part, cosine will give you the x part. So really you just set it up so you already know. You already know what in our notes here is the blue and the red. Perfect. Third part, make the t-chart for the vertical and horizontal parts. All right. Figure out, this is going to sound weird. Step 4 is figure out the, quote, master, unquote, equation. This is, and here's kind of my explanation. It's what you'll plug everything into at the end. So like, for instance, if I need to find out how far will a cannonball make it before it hits the ground, well, how far, that's x. This is literally the only equation that has x in it. This would be the master equation then, and your goal would be finding the x velocity and finding the time. And you'd have to probably use the vertical part to get the time, and you'd have to use cosine to get Vx. And that would kind of be the idea. So figure out the master equation. This is what you'll plug everything into in the end to finish the question. Step 5, find all variables for the master equation. Now that's a lot easier said than done, I know, but kind of in the example here, well, if this is your master equation, the components you need are Vx and t, right? So find all the variables for the master equation. And then final step, use or plug into the master equation. Done. That's really it. This is kind of the overall steps. I would star this, I would circle this, I would do something here so that you know this is kind of an important thing. This is going to be like a great overall set of steps to be able to reference and follow. And so that's it. Thanks for listening. Hopefully, this makes sense. Stay tuned to our next video when we'll be going over a sample problem using these steps.